Okay, you're gonna have a little over 5 minutes to get your mealworms out, get your groups. Mealworms out. You need to be collecting observations in your lab notebook. Okay, as well as you need to make sure that you are collecting digital images or video for your digital story in your mealworms.
Is it possible to hold those? We need to replace those juices.
Yeah, let me replace theirs and see how much left I have, okay?
Is it possible to hold our little insects?
Yeah, you can hold the beetles.
Miss Barnett.
Yeah.
Can I go get my sanitizer?
Y'all are still very clear. Yeah. Let's go get a paper towel. Okay, make sure you get a good observation. We also need to make sure the mealworms have plenty of a food source for the weekend.
Miss Bona does not live in here anymore.
What happened? What is that?
A beetle.
Well, we had 2. It's okay, Mallory.
Sorry, it scared me. I saw some legs moving. I was like, what? Oh, wait. Probably don't. Miss Bona, we don't have it. Here. It's just. Oh no, it's one more.
Oh my!
Oh, I touched it.
Oh,
Don't
touch it. Mallory, you're a scientist. Stay focused. You have a beetle. You sure do. Check out like does it fly? Hey guys, y'all may need to get some lettuce and bring it to me. Get some from the salad bar. Get some from the salad bar. Get some from the salad bar, Mallory, and make sure I get it by the end of the day. Otherwise, your mealworms are gonna not have enough food. You just have 4 in it, right?
It's only 1 egg.
Oh, I'm not touching them.
You don't die?
Yes, I cannot do.
But not just from the lettuce one, everyone stayed alive. It's no poo, it's just shit. No, you're not good.
Everybody lower their voice. You're talking just to your lab group. You're staying on task. You only have about 2.5 minutes. I will bring them some more. I'll bring some more.
Yes.
Okay, I'm
He's turning into a beetle. Yes, so
I can assure you and tell you that the beetles are non-aggressive critters. Okay.
they're so cute.
And they will not bite you.
One just flies up and jumps on your face.
But be careful. Remember, you signed an adoption certificate saying you would treat your mealworms.
So do we
No, Tommy, he just throws them in there. Is this apple?
I'm scared.
That was just a regular beetle. And it was kind of weird because these said that they all stayed alive.
It's not.
And then that all those, I don't know what happened.
Can I see the beetle?
Okay, if you need apples, you need to come over new food sources. You need to come to me and get that for the weekend. Make sure your mealworms have plenty of food source because we've got a long weekend. Then you come to me.
Where's our apple?
You need 2 pieces? Yes, you do. Is that okay?
Don't touch it. It's so easy. It's It's not ready yet. We're going to put it Its legs are starting to move.
Okay. Noah and Mallory, y'all making a good, I don't see your lab notebooks out. You don't see you writing up a good observation. I know there's lots of exciting things happening with our mealworms, but we still have to be subjective. effective as scientists in collecting our data. Now we've got about 30 seconds. When the timer, when the timer goes off, I want you to put your mealworms back. Okay, if you've not had a chance to write up your observation, you need to make sure you do that by the end of the day before you forget, okay? And then I want you to make sure you get your student-generated models, and I want you back in your seats with a writing utensil and ready to take notes, okay? Timer goes off, mealworms up, okay? Student-generated in front of us, models, and ready to take notes.
I'll be back next week. It's going to be
Why did you do it?
Can I go do my lunch break and get my...
Yes, quickly.
Okay, quickly. Okay, back in your seats. Have your student-generated model with you. Ready to take notes. Mealworms, you go back. Zoe, Gabby, I know you love your mealworms desperately, but you gotta let them go for the day, okay? Come on, guys, quickly. You're wasting precious time. We're on a little bit different schedule, so I lose a couple minutes that are precious to me. No. Okay, your student-generated model should be out. You also need to get out your study packet. Get out your study packet.
Oh yeah, I'm going to tell you about this today.
All right, because we've had kind of some funny schedules this week, and I don't do this very often. I just felt like the basketball team is going to state, and I'm feeling joyous and excited about that. If switch with your partners, your study packets really quickly. Switch. If your partner did at least 75%, so they could have missed up to 5 questions. Okay, they could have missed up to 5 questions, and that would still put them at 75% of the study packet. If they did 75% of the study packet, they get 100. Okay, mark 100 on them. If they did not do the rest of their study packet, they want to lose 10 points and turn it in on Monday. Okay? So who, Mallory, you still need to turn it in on Monday?
I guess so.
Okay.
But can I have some help on this one?
Sure. You need to come. You schedule with me to come in when during the second times. Okay.
What if they...
Less than 75%, they want to keep it and finish it and turn it on Monday. They're only losing 10 points.
So, what about if they... There's 16 questions is less than 75%.
Do they miss more than 5?
Oh.
Right? More than 5 is less than 75%. Okay? So, Corbin, is that yours that you need to finish? Okay. Corbin, you still owe me one. Mallory and Corbin, correct? You'll still owe me one on Monday, okay? And Wayman. Rachel, will you hand yours to Drew? He knows what to do. Hand your study packet to Drew. Real quick. All right, Rachel, you got yourself 100. Good job. Okay? And we'll go over, make sure we have all the correct answers and go over questions on Monday. So anybody has questions, just write in the questions you had over the packet, and I will go over those questions on Monday. Okay? All right, so good job. Those of you, Corbin and Mallory, don't forget to make sure you finish that packet so you can get at least a 90, okay? So, yes.
What do we have for fourth period?
Today you have fourth period, you'll have PE. Well, or study skills if you have a sport, you'll have study skills. So if you need to come to me, you can. Okay, so today we're going to continue on talking about plate tectonics, okay? And we're going to look at how each of our stations is affected, okay, and plays into the theory of plate tectonics, okay? We're going to hear first from our favorite robot, okay, and human friend, Tim and Moby, okay, and see what they have to say about plate tectonics. I asked you to make sure that you had your student-generated model out, okay, for a couple of different reasons, okay? One, you may, as we're talking and watching the video, or as I'm lecturing, you may realize that your model is not quite accurate, and you need to make some changes to it, okay? So that's what you can do while we're talking. Oh, or maybe you need to write a little note. Oh, this happens on your student model. So that way we're making sure you really understand. I expect everyone's student model to be completed by Monday. It's due Monday. So you're going to take your student model with you, okay? And you're going to make sure that it's completed. And I will be collecting them for a daily grade on Monday. As well as your student model being due on Monday, you have a take-home quiz on plate tectonics. That means everyone should get 100 because it's open book, open notes, okay, on the quiz, okay? So use your lesson pages. Do not fall into the temptation of Googling an answer because most likely it might give you a slightly different answer than the lesson pages do, okay? Remember, all the answers are where? In the lesson pages. I guarantee, promise you, never been wrong on this one, okay? So, if you have a question and you're stumped on the quiz, go back and read through your lesson pages again online, okay? So, the answer is there, I promise you, okay? You might even find some of the answers as I'm speaking and lecturing today, okay? Sense? Any questions?
Yeah.
We're good to go. So, as we're talking, we're thinking about our student-generated model and things we need to change, and our quiz as well. Aqua.
Can I have another one of those papers that gives you the instructions for drawing it?
I will see if I have one additional copy, okay, after class, please. I believe I do. Gabby. Oh, Gabby will share hers. Thank you, Gabby. That's right, because you were awesome and finished it yesterday. Good job. Okay, let's see what Tim and Moby has to say about plate tectonics. Yes.
Dear Tim and Moby, what in the world is a Pangea? From Dan. Sounds like we need to get into the theory of plate tectonics. If you look at the shapes of Earth's continents, Africa and South America look like pieces of a puzzle that could snap together. This supports the theory that all of the continents were once one big continent called Pangea. Scientists believe Pangea existed about 200 or 300 million years ago. Then it started to break apart, eventually forming the continents we see today. Now, it's not like they were floating. The ocean floor was moving too. The outer layer of the Earth, or crust, is broken up into about a dozen major and many minor tectonic plates. These plates float around on a layer of molten rock called the outer mantle. When the plates move, continents shift along with them in a process called continental drift. This motion explains why fossils of the same kinds of prehistoric animals were found on the northeast coast of South America and the southwest coast of Africa. Well, when the continental plates shift, you hardly ever notice the ground moving. Continents only move a few centimeters every year. Oh, yeah, I'm getting to that. Lots of things happen at those active boundaries between plates. Volcanoes, earthquakes, mountains, and trenches are all results of movement along plate boundaries. Divergent boundaries are where plates are moving apart and new crust is created by liquid rock pushing up from the mantle.
Okay, so divergent plate boundaries, we talked about that in our student model. The plates are moving away from each other. But the thing I want you to make sure you understand, now is there now, once the plates move away from each other, is there now a big crack and hole where we can go and see the mantle?
Yes. Well, no, because
No, what's going to happen, Drew?
The magma's coming up.
The magma's coming up. Why is the magma coming up? not suction.
Convection.
The convection currents are heating it, moving it, because it becomes what? More or less dense as it moves up. Less dense, it floats up, okay? So that's why the magma's coming up. And then once the magma comes up, it cools and it forms new crust, okay? Lots of people have misconceptions and think when the plates move away from each other that there's now a big, huge crack, okay? That's not true because the Earth kind of naturally recycles our crust, okay? God designed it in a really special way to be able to do that. Mallory. Wait for a little bit, okay?
Convergent boundaries are where plates are moving toward each other, and sometimes one plate sinks or is subducted under another. Transform boundaries are where plates slide horizontally past each other and cause friction. These plates are always moving, slowly changing the face of the Earth. Who knows what the world could look like in another couple of 100 million years? Oh yeah, sure, Moby. Well, it's not impossible, but it's unlikely. You're insane.
I don't think the Earth's going to ever look like that. But I think he's a very silly robot. Okay, so... Oops, there it goes. Okay. Hold on, let's start that over. There we go. Okay, a little technical glitch. Okay, so the theory of plate tectonics. Now, they introduced a word at the very beginning of that Brain Pop video. They introduced something that you may or may not have heard, okay, before, that talked about that the Earth actually, we thankfully looked at like a super continent, one big, huge chunk of land. What was that word that they introduced to us? Joshua.
Pangea.
Pangea. So we think of this, that the supercontinent, we call it Pangea, okay? And when you look at our continents, it makes sense. It looks like there's a jigsaw puzzle going on, right? Okay? We decided that what two continents look like they'd fit pretty goodly. What were those? South America and Africa, if you put them together, Lizette likes the reference to South America, right? So South America and Africa look like they would fit together pretty closely. And even though they don't fit perfectly, what would be a cause of maybe them not having the perfect lines anymore?
Ooh. Weathering and erosion.
Weathering and erosion. Ah, the rock cycle comes back with us, okay? So we can see that those puzzle pieces, though, look like they do. So we think that there was originally this supercontinent that existed, okay? So we want to make sure in this lesson that we understand what the theory of plate tectonics are, the three types of plate boundaries, okay, specifically, and why do tectonic plates move, okay? So we want to make sure that we isolate that. Wow, lots of vocabulary in this lesson, but don't freak out because this is a lot of vocabulary you've seen before, okay? We've already been talking about plate tectonics now for several days, right? Okay? You should be familiar with the word divergent, transform, and convergent plate boundaries. Where did you see that word before this week? Y'all seen it this week. Where was it? Huh? Lesson pages. Where else? Where else? Our model, right? Our model talks about all those three different plate boundaries, right? Okay, so you should be having some deja vu here. Lithosphere. Who remembers lithosphere? Drew, what's a lithosphere?
It's where like the uppermost mantle and the crust.
Right. Remember when we talked about the layers of the Earth and we discovered that the crust and the uppermost part of the mantle is the lithosphere. So that's not a new word for us, okay? Subduction, you should have read that in your student-generated model, right? Okay, so we know what the word subduction means already. Convection. We actually got to witness two types of convection currents being created in our classroom this week. What were the two types of convection currents or locations? Which stations had convection currents? Name me one. Right there. Remember we looked at the water was boiling and it was moving the plates. Those were convection currents going on. Where was the second station? My magic raisins. They're really not magic. They're just using science. Now, those two convection currents were created by two different processes. The raisins. Was the raisins using heat?
No.
Nope. No, what was it using?
Carbonation.
Carbonated water, the bubbles, okay, the gases. Now, when which station most likely resembles the way the Earth's convection currents are created? Which station? This station with the foam and the water, or the one with my carbonated water? Rihanna? The one with the foam and the heat, because that's how our convection currents are created, because we know as we go deeper into the Earth, what happens?
It gets hotter.
It gets hotter, okay? All right, and then we're going to talk about ridge push and slab pull, okay? And those are going to make more sense to us by the end of today. All right, the theory of plate tectonics was proposed in the late 1960s, okay? So is it fairly new?
No. Well,
Probably for most scientific theories, okay? So actually, do some of your grandparents, did they learn about plate tectonics in school? No, they didn't, okay? Most of your grandparents are probably older, okay, or were born, and they were probably in school before even plate tectonics were existed, okay? So this is a fairly new theory, and actually the gentleman that came up with plate tectonics, when he proposed it, he actually, one of the first things that they came up with plate tectonics is the gentleman that actually proposed Pangea. But he didn't know that plate tectonics existed. He just thought it looked like the continents fit together like a big jigsaw puzzle, and everyone thought he was kind of crazy because they're like, well, how did it break apart? And that's where plate tectonics came in, and plate tectonics helped us prove that Pangea existed, okay? So this theory states a couple of different things. The Earth's surface is made up of rigid slabs of rocks or plates, and these plates move with respect to each other over the Earth's hot and semi-plastic mantle. Why is this a theory and not a law? Mallory? It might be able to be proven wrong. What else?
We cannot observe it.
We can't directly observe it and test it, right? Because we can't go down into the mantle. We can't get that deep. So exactly. So it's still a theory. So it might change, one, okay, as science is always changing. And we can't test it to prove. Like we know, we studied some other laws. What were some of the laws we studied this year? Y'all remember any one of the laws? Newton's laws of motion, and we can test those over and over and over again, and they always happen the same exact way. And that makes this a theory because we can't test it. So, what is plate tectonics? Someone sum it up for me. Not looking at your notes. Drew, what is plate tectonics?
The theory that Earth's plates are rigid slabs of rock and they move with respect to each other over Earth's.
You just gave me the definition in your own words. Explain it to me.
Oh, okay. There are these plates on the Earth and they move.
They're moving, right?
Yeah.
Now, are they moving like super quick?
No.
No, it's really, really slow. Okay, it's a slow process. So, lithosphere. Geologists use the word tectonic to describe the forces that shape the Earth's surface and the rock structures that form as a result. Okay. So when they're talking about rock structures, maybe what are they referring to? Rock structures. What do you think?
Like mountains.
Like mountains, right? We know that plate tectonics, several things that plate tectonics do. What were the 4 geological phenomena that occur, events, okay, or landforms that can occur because of plate tectonics? Wayman, you got this one?
Mountains, volcanoes. The big thing with the hole and
Trenches, yes.
and then what's the
Shake, shake, shake.
Earthquake.
Earthquake, very good. All right, earthquakes, okay? So at these plate boundaries, we see these results because of tectonics, which is that movement, okay? We know that lithosphere is just that rock layer, okay, in the uppermost part of the mantle. So what are my plates made out of? Rock slabs, but what is, in other words, that rock slabs that I could use?
lithosphere?
Lithosphere, it's my lithosphere. My plates are my big chunks of lithosphere, okay? Very, very good, okay? So we can see that those are what are moving, okay? So we now, remember we talked about the layers of the earth, and we discovered that not all the crust is the same, right? Okay, we know that we have the ocean, okay, crust are going to be thinner, okay, and then the continent crust are going to be thicker, okay. Now, why is the oceanic crust where it is and the continental crust above it? Why?
I think it's
You think it's because of density. Exactly. Remember density, our friend density? Maybe some of y'all, it was your enemy, okay? Right, density. And we even looked at density a little bit this week. What station did we look at our density? Wait, I'm going to pick up someone who's Corbin.
You looked at whatever this station was.
With the test tubes, right? And we looked at the bead and how it moved through the different fluids, okay? Because of their relative density. And we discovered that the denser liquid, what happened to the bead in the densest liquid? What had happened to it? It, like the one that floated on the corn syrup, right? It floated because the corn syrup was our densest material, and it floated. And what we call when something floats is, and we call it, it's based on buoyancy. Okay, you might have heard this. We talk about that when we talk about like ships, okay, and their ability to float. It's because of their buoyancy, okay, because of the thickness of the liquid, okay. The Earth's tectonic plates are large pieces of this lithosphere. We know they fit together like a magic jigsaw puzzle, okay? All the plates fit together, okay? Not the continents, we're talking about the plates, right? Now, are the plate boundaries always by the continents? No, right? Where's some of our plate boundaries go through? The ocean, okay? So keep everything, okay? We know that below our lithosphere, I know y'all loved all these layers. Y'all remember having to write them out on the test?
Oh, yes. Loved it.
I know y'all loved it. It was so much fun.
It was awesome.
Awesome, okay? But remember, but it's good for you to remember because look, here it comes again, okay? That's why I have you do those kind of things because I know you need to know it for the next lesson, right? Okay? Miss Bonai doesn't make you learn things that you don't need to know, okay? So we see that the asthenosphere is that hot material that's like behaves like plastic. Now, make sure you understand in science when I talk about something being plastic, okay, typically I'm talking about how it behaves, okay? That we can bend it without breaking, okay? It doesn't mean that it's actually plastic. So when we use that term plastic, the mantle is not made out of plastic. What is the mantle made out of?
It is made out of liquid.
Not metal, rock, liquid rock. Mallory, do you have a question?
It's kind of in the middle, but like, can't you kind of tell? Yeah, it is a question. Can't you kind of tell that it does go pretty slow for the Pangea to separate since it's like 300 million?
Exactly. She made a great observation. Can't we prove and see that the plates are not moving very fast? Because look how long it took for Pangea to break apart and form what we know as Earth. And, you know, I don't notice any difference in the way the Earth looks for my purposes, okay? But my great-great-great-grandchildren will see a difference in where the continents are because there is moving. But it's moving really, really slow. And sometimes that makes it hard for us to understand plate tectonics and how everything's moving because it's so slow, right? Okay, so it's not a fast process, okay? It's very, very, very slow. Good point, Mallory. I love it. All right, everybody get your maps out. Remember the maps we did at Station 6?
Oh, yeah.
Here they come back again. I had a couple, if you don't have your map, I have a couple that people left. They don't have names on them. Okay, so if you're missing your map, this may be one of them. Okay? One's in red, one's got red writing, one's got red boundaries, and one's got green boundaries. So that sounds familiar if you come get it really quick. Make sure you put your name on it, please. Name, name, name. Y'all driving me nuts with the no names. Okay, Mallory. Oh, you weren't here that day. Here, your line's already drawn for you. You get these one. Okay, now what I want you to do is you notice these arrows. What do you think these arrows represent on this map?
Plate boundaries.
They are plate boundaries, but what are they representing? Gabby?
The movement.
The movement, okay? What do you think I want you to do?
Label. Mark it.
Draw this. Yes, mark these, okay? Because I want you to understand, okay, that the way these plates are moving, okay? Because the way the plates are moving is how we tell what kind of features the land's going to have, okay? Or the type of phenomena that are going to occur, okay? Certain types of boundaries create certain things. Like, for example, what kind of boundary is going to create mountains?
Convergence.
Convergence going to create mountains, right? Because they're going to push up, okay? So here we see, okay, so when the arrows are pulling away from each other, what kind of boundary do we have?
Divergent.
Divergent boundary, okay? Now, I want you to notice, because this is kind of cool, okay, if you look at, for example, South America plate and the Nazca plate, okay, they're convergent here, but on the other side, it's divergent, right? So it doesn't mean the plate is, since it's moving, right, that makes sense, okay? If it's moving in this direction, right, towards this plate, it's moving away from this plate. Do y'all see how that makes sense? Okay? They're moving. Now, this is not fast, right? A few centimeters every year is about it. Centimeters are pretty small, we've discovered. Okay, in some places it's even less than that. Some boundaries are what we call non-active boundaries. We're just not getting a lot of movement going on. Now,
I have a question. Why is the map not show all of them like the
it only has the major plates. Your map has the major plates. I didn't do the minor plates, okay? So you just label the major plates.
Okay.
But there are minor plates, okay? And if you want, you can put those on your map if you will, okay? So now what did we discover at that station with our map? Because we noticed they had lots of little dots on it. What were the little dots on the map that I gave you? Corbin.
Plate tectonic.
Not plate tectonics, Lizette. They were earthquakes. And where did we see most of the earthquakes occurring?
In the Pacific plate region.
Well, some, but specifically a little more broad. Wayman.
Plate boundaries.
At the plate boundaries. Remember, it almost helped you sketch out your plate boundaries because there's little dots that represented all those earthquakes, okay, that were moving because of plate movement. Okay, a divergent plate boundary. Now, what should you be doing as I'm talking about this? Taking notes, but also I told you working on something else.
Yeah.
Your model, exactly. You can correct your model if you don't have something right and make notes to make sure your model is more accurate. Okay? So divergent plate boundaries form when two plates are separating. Okay? So we see when the seafloor spreads at a mid-ocean ridge, lava erupts, cools, and forms new ocean crust. So remember, there's not a big hole, okay? There's now new crust that's forming, okay? Divergent plates can also exist in the middle of a continent where they pull continents apart and form rift valleys, okay? So sometimes it happens on land, sometimes it happens in the ocean, depending on where the plate boundary is going through, okay? And so we can see these things, all right, in the continents, and we see the rift valley. So they're moving apart, okay? Here we see the asthenosphere comes up because it's what? Magma, and it's less dense because of the heating, okay, that's occurring, okay? And so it comes up and fills in those holes, and it cools and forms new crust. I really wish I had a clicker so I didn't have to walk. All right. All right, a transform plate boundary. Now, we actually watched a video about a transform plate boundary and a particular fault. What was the fault's name? Corbin.
San Andreas Fault.
The San Andreas Fault, which is in California, okay? So transform plates are actually sliding past one another, okay, in opposite directions. And as they move, remember, they kind of get stuck, okay? They get stuck on each other, okay? And what happens is it kind of stops in the pressure and the force. Wait a minute, I need your head up. What happens is that stress builds up, okay, right? And it keeps building, like I'm pushing something. Remember we talked about a heavy item, you're pushing, and eventually it gives, right? That's what happens, okay? It'll move apart, and that's going to create a sudden release of energy. And what do we call that sudden release of energy? Earthquake. It's an earthquake, right? It does create a seismic wave that we can measure, okay? But it's an earthquake specifically, okay? So, what kind of plate boundary do we see earthquakes most likely at most of the time?
Transform
boundaries, okay? They're associated with a lot of earthquake movement. Now, I asked you in your pre-test, okay, a lot of y'all, if we could predict large earthquakes, okay? Now, we know that, like they said in the video, do they know that at the San Andreas Fault there's a lot of pressure and stress? Do they say that? Yes. Do they say they know exactly when the earthquake's going to occur?
No.
Anytime. We know it's going to happen. We know we can kind of guess a general idea of like it's coming sooner, but we don't know, okay? It's not like weather where I can say, hey, there's a hurricane going to be hitting on Tuesday, okay? You need to evacuate. Earthquakes aren't like that. We just don't have the technology to be able to tell when that release of energy is going to occur. But even like the one in Haiti, there have been scientists that have predicted about a 7, okay, magnitude earthquake would hit, and they had predicted it within like a 2-year span, okay? They've gotten pretty close, okay? So we're getting better at doing it, but we still can't do it to where it's like down to the day. Drew.
How can I draw an earthquake?
How can you draw an earthquake? You can do squiggly lines.
Okay.
When we're swimming. You can model squiggly lines is good for an earthquake. Or you can say earthquake. You can write it out if you need to. Gabby.
I think the only way to predict an earthquake would be unless in the advanced technology with sensors on the ground.
Well, I mean, there are sensors on the ground, but the problem is it moves suddenly, right? It's like building, and then it just jerks away. We just don't know when that's going to happen. Now, because of seismography, we can tell when an earthquake, when there's been movement and waves and earthquakes occur, even the little ones that no one feels, okay? So we do have sensors in place that tell us. And GPSs, remember, that shows the movement, but no necessarily able to predict. Corbin.
What was the seismic activity monitor? What the Richter say?
Oh, you mean the magnitude? That's the Richter scale.
Oh, okay.
Richter scale. Good recall. Mallory.
So if the scientists thought it was a 7 2 years before it happened, what was it really?
It ended up being it read at a 7.
Oh.
They said they predicted a 7.2, and it was a 7. So they're actually very, very accurate in their prediction. The problem is we just don't know when. But they could tell that by some of the geological features and the changes that they saw, that they knew the stress was building. So they can tell that there's stress building looking at the landforms, the fault lines. Okay? Wait a minute.
I think, actually, I know there's a seismograph at Rice University.
There is a big seismograph at Rice University. It's a really cool looking machine. It kind of, it has a needle and it goes and shows. And so they measure seismic activity in Texas. It's very, very interesting. So that would be a cool field trip one day, maybe. All right, so convergent plate boundaries. They form where two plates collide. The denser plate sinks, right? Denser sinks, okay? Less dense, floating, okay? And this process of it sinking, okay, causes what we call subduction. All right, and that area that it sinks in is called a subduction zone. So we have the subduction zone, and that's where the plate boundaries, okay, where you have a convergent plate boundary occur, okay? See, density is so important. Aren't you glad I've been teaching you all about that? Now, an ocean to continental convergent plate, okay? Which plate's more dense? Oceanic crust or continental crust? Which one's more dense? More dense. Corbett.
The continental.
Continental's more dense. Does somebody have a different opinion? Mallory.
I think it's the ocean.
The oceanic crust. Why do you think it's the oceanic crust that's more dense?
Because the continental is below the ocean, and so the water would be less denser because it's on top of it.
Okay, so you think it because of it's lower and the continent's higher. You're exactly right, okay? Remember when it layers, right? There's layers, the more dense materials on the bottom, lighter stuff's on top, less dense stuff, okay? So what we have is the oceanic plates, okay? So the denser oceanic plate subducts, okay, goes under the edge of the continental, creating a deep ocean trench and a line of volcanoes. So what feature do we see on this? We said transform boundaries. We see what? Transform boundaries. What do we see going on?
Rubbing against.
Rubbing each other, which makes what kind of phenomenon?
Friction.
Earthquakes, right? So here, when you see volcanoes, you know what kind of plate boundary?
Ocean to continental.
Convergent, right? Exactly. Okay? So what happens to what? Earthquakes usually in the oceans a lot of times too. Plate movement within the ocean creates.
And what does that make a tsunami?
Huh?
An underwater earthquake?
Yes. Okay, so what happens, okay, is I want you to realize that what happens is this oceanic crust goes under, okay? It actually gets down here and it eventually melts and becomes new mantle. So the earth kind of refreshes its crust constantly through these changes, okay? So God kind of set it up where, so it's not like we ever going to run out of mantle, right? Because as soon as the crust is divergent and new mantle's coming up and cooling, making new crust, there's also somewhere else in the world a convergent boundary where the crust is going under, melting and becoming fresh mantle. Does that make sense? So we'll never run out of mantle. God was a clever designer. Valerie.
So subduction helps make oceanic trenches?
Correct. Mm-hmm.
That makes more sense.
Now we see continent to continent convergence, okay? So when two continental plates collide, neither plate is subducted because of what? Why are they neither one subducted?
They're the same density.
They're the same density. Excellent, Drew. They're the same exact density, okay? And so what happens, instead of one going up under, okay, they're the same density, then you see them in colliding and pushing up, okay? Excellent. I see his model. Wayman's showing me his model. Exactly. And that's how you get mountain formations, okay? So mountains, those big mountain chains. In fact, some of y'all did some, the Alpine Fault, okay? What did you discover? What's along the Alpine Fault? Somebody do that one? Alpine mountains, right? Chain, okay? So we see that we create mountains, okay, by the plates pushing up. That's only at continent to continent convergent. So continent convergent creates mountains. Oceanic to continent convergent creates
Trenches.
and
Earthquakes.
Volcanoes.
exactly. And transform boundaries create transform boundaries. San Andreas Fault. Transform boundary. Earthquakes. So, 3 types of plate boundaries. What are they? Someone name them really quick. Noah, what are 3 types of plate boundaries?
3 types of plate boundaries.
One's divergent. I'll get you started.
Convergent.
Divergent, convergent, and starts with a T.
Transform.
Transform boundaries. Excellent. Okay, scientists can measure fast continents moving using a network of satellites called the Global Positioning System. We shorten this for what?
GPS.
GPS, just like you have in your car, same technology. Okay? Or your phone, okay? Because plates are rigid, tectonic activity occurs where plates meet. Okay? That's where we see those tectonic activities, the pushing and the force. Volcanoes form when plates separate along mid-ocean ridge or continental rift, or collide along subduction zones. So we always have convergent, okay, for volcanoes. And mountains always form when 2 continents collide. So if you see a mountain, you know that's a convergent plate boundary, right? It's 2 continents coming together. We will pick up here on Monday. You want to make sure you're here Monday. We have a great day. You may have a lab that's edible. Take your model and you're finishing it.
If we finish it,
You can also soda listen pages.
It kind of gave it away. It was a picture cute. I'll put it in my notebook.
Wait, what
We'll
was
take
that?
it on Monday. Bye, guys.
Bye-bye.
If those cards have PE, do you want me to still come?
You can. It's up to you to check with this
We have to arrest Jason.
No, we don't. Well, we don't.
Do it. You can go check this
Because I
card
already-
and Coach Jones can read it.
Y'all run on Tuesday.
No, the people from Steady.
Have a great long weekend.